Hi, and welcome to the latest episode in the long-running soap opera called Realistic Business Forecasting. Today, we're finally going to actually do a regression. We're going to start with a very simple version, and then we are going to make it more complicated. So let's get cracking. Now, before we actually do any regression on Excel, you need to have this thing called the Analysis Tool Pack installed. It's actually included in Excel, so it's just a matter of activating it. Now, I've actually provided the URL for instructions, but you can see the URL is pretty horrendous. The easy way, perhaps, is just to do a search in Google for Install Data Analysis Excel, and you should get a very similar article, or perhaps this exact one, which will help you install it. It is a very simple, straightforward process, and most importantly, it's free. So let's actually have a look at a simple example of a regression. Now, I've taken one of my favorites, which is crops. So we're going to assume that the amount of yield that the crop produces is dependent on how much rain falls on a particular bit of land. And what we assume is that the more rainfall there is, generally, the better the yield will be. So what we have here is a set of 10 observations, which are, let's say, taken from different parts of the country. So there's no time element involved here. So this is a snapshot of 10 different experiments, 10 samples, as it were. Now, before you actually do any analysis, you should just look at the data. And what I've done here, I've just done a simple scatter diagram. And you can see that for the range of data that we have here, it looks pretty linear. So it's of the form y equals a plus b times x, where y equals the yield and x equals rainfall. So what does a regression actually do? In its simplest terms, a regression will fit what is known as a line of best fit. And I've actually shown that with the red line. You can actually generate just the line itself by adding a trend line, a linear trend line, to a scatter diagram in Excel. But the way that this trend line is calculated is that it will take the vertical distances from each point to the red line. It will take the square of the value, so you don't have a problem with positive or negatives, and add them up, and it will find the line with the minimum sum of squared values. I hope that's not too complex. It's not something you need to know, but I think it's useful to know what the regression actually does and how it works in its basic form. So to carry out the regression, I've just given a quick sample here, but I don't want to do a full tutorial on this. There are plenty of those online. So all I have done here is I've shown how you highlight the Y range, which in our case is column F, the X range, which is column E. Now, I always include the labels. So the range of my data is from the second row down to the 12th row. So E2 to E12, F2 to F12. You then need to click Output Range. Just make sure you select a cell where there's plenty of spare space, nothing else going on. And then you should come up with something like this. Now, I've actually done a bit of color coding, but the actual data, which you can see on the screen here, is what you will get from the regression analysis. So I just want to go through these results. It is quite important. First of all, let's look at the equation, and this is generated from the last bit of the output. So the equation in this case is the coefficient, the intercept, which is 5.87, plus 3.61 times rainfall. And I want to actually look at these three other things: t-stat, p-value, and low and upper 95 confidence. What we're trying to determine here is whether the values we have generated, the coefficients we have generated from the regression process, are significantly different from 0. And each of these three, the purple, the blue, and the green, tell us the same thing. So perhaps the easiest way to process is, as long as a 95% confidence interval in green does not include 0, then we can say that our coefficient is significantly different from 0. Now, one thing I want to point out with this first set of results is that what this equation is saying is that if rainfall is 0, then the yield is 5.87 plus 3.61 times 0. In other words, you get a yield of almost 6 if there's absolutely 0 rainfall. That's not really plausible, is it? If there's no rainfall, then there'll be no yield. And I've talked before about this business of the relevant range. If you actually look at the range of data that we had for rainfall, you see it doesn't go all the way down to 0. So this result is valid for the range of data we have. And I'll be coming back to that in future. Let's look at a bit more of this output. What this is telling us is that 81% of the variation in yield is attributable to the variation in rainfall. That is quite a powerful result. We can ignore this middle bit because it only applies when you have more complex regressions. And I just want to come back again to this issue about the significance. The other way you can look at the significance is whether the p-value is less than 0.05. And you can see that in both cases, the p-value generated by Excel is well below 0.05. So it's telling us the same thing as a confidence interval, i.e. that both coefficients are significantly different from 0. So having actually got our model, and we can then compare it with actuals and check the residuals. Now you can see that I've actually ordered the yield from lowest to highest. And then the model generates these values. It's using the equation of the constant plus coefficient times rainfall, and we get a stream of residuals. So what do these residuals look like? Well, they don't look too bad. They're not increasing as y gets larger. They look pretty random, so that's good. That's the thing the two key things we look for. We look for no obvious pattern and no obvious trend. So this is looking pretty good. Now, let me come back to one of my favorite bugbears, which is intercept and slope. I actually use these horrible things, and I just wanted to show you that you do get exactly the same values as using the regression. But this is all you'll get from using intercept and slope. It doesn't give you any of the valuable extra information which the regression function does. So that's why do not use intercept and slope, please. Always use data analysis regression. So let me come back to this business about the relevant range. How realistic is the analysis? Now, I'm not an agricultural expert. I know someone who is, but it's not me. Now, I'm assuming you need a certain minimum amount of rainfall to actually get some crops growing out of the ground. And I think we can be pretty sure as well that if there's too much rain, like major floods, it's going to wreck the crops. So I'm suggesting that the curve looks something like this. For those of you who are familiar with statistics, you will recognize this as a normal distribution, which it is. But I just wanted to try and illustrate what I consider to be the overall range, the maximum range that yields will have with the maximum number of possible values from rainfall. And I reckon it is something like this. So starting from 0, there's probably some optimal value here. And then as the rains get heavier and heavier, then the yield will fall and it will go down to 0 when the rain is excessive. But we actually are using a limited range of data. And for the limited range of data, I suggested that the pattern looked like a straight line. And I've tried to illustrate it here. Let's say that our range of data is the orange line. And you can see that the orange line, if you put it next to the curve, the orange straight line is an extremely good approximation for that section of the full curve. I also said that you can perhaps extend the range a little bit if you're going to do forecasting, but not too much. And again, the little blue bits here, I hope do explain that. You can see that as the blue line extends, it gets further away from the curve. And here, what will happen is if you extend the blue line, it will go below the curve. So for the range we have, we are fine using a straight line. We can go a little bit outside the range, but not too much. It is pretty subjective, but the important thing is not to go too far outside the range of data that you have from historical observations. Well, I hope that was useful. What we're going to be doing in the next session, number 7, is we're going to be introducing another variable other than rainfall, and that's when things really get interesting. So thank you very much for listening. If you've got any comments or queries, please put them in the text box, and it's goodbye from me.